Hello, I'm going to be presenting the paper titled Reliably Learning the ReLU in Polynomial Time. This is joint work with Varun, Adam, and Justin. So let me start by defining what a ReLU is. It's basically a unit in the neural network which takes an input x and weight vector w and outputs the function max of 0, comma w transpose x. So this is a commonly used activation function in a lot of neural nets nowadays in practice. So the motivation to understand how we can learn even a single ReLU unit is important because to understand these deep neural networks, we need to first understand this basic unit. Also, the less obvious motivation is that it has interesting applications. Other activation functions like sigmoids have recently been shown that graphical models reduce to learning sigmoids, which is an interesting application of this. So now let me discuss the learning model that we're going to look at. So in all our settings, we're going to consider the agnostic setting where there may not be a function that actually fits the data. So there are two fundamental problems in learning. One is ordinary least square regression, which is basically fitting the best possible linear function to the data. And there's the problem of learning half spaces, which is finding a half space that correctly classifies as high a percentage of the data points. It is known that least square regression is easy, while learning a half space is hard, and there are a lot of hardness results known for learning half spaces. So now ReLU is sort of halfway between like a half space and a linear function. It's like a one-sided half space. So the motivation for this work is that ReLU seems like it should be somewhere in between in complexity of a half space and a linear function. Another question that it raises is what kind of model or loss function do you look at? Because it's like either you consider the 0-1 loss or the squared loss. So we define a model called reliable learning, which is an extension of the reliable learning model by Kalai and all for Boolean functions. So it is the motivation is to capture these dual losses. So on one hand, we have the loss, which is corresponding to the 0 labeled points, which is basically the false positive error, and there's a loss corresponding to the positively labeled points. So what we want to do is we want to minimize the 0 loss and have it as low as possible while still simultaneously being good at the other data, the positive labels. So an intuition for this kind of application is supposing you have a lot of comments on your news website and you have spam. So what you want your spam to always be marked correctly, and you still want to do good on getting some scoring for how relative your parameters are. So this is kind of a motivation for it. Also observe that this is stronger than agnostic learning because we can just tweak the labels of y to never be 0 by adding some noise. So that the first loss is automatically satisfied by 0, and so the second loss just reduces to fitting the best possible function. So our main results are basically that we can show that we can reliably as well as agnostically learn a ReLU. In the improper setting that we output a hypothesis that is not strictly a ReLU. This is possible in time which is polynomial in the input dimension but exponential in the error parameter. Our result holds for any distribution on the unit ball, and contrasting to the best known half space learning algorithms that take time that's n to the 1 by epsilon squared and require assumptions, we don't require any distributional assumptions. We also extend our results to higher depth network using composition results due to Zhang, and our results also extend to sigmoidal networks, and interestingly for sigmoidal networks we get a polynomial runtime in all parameters. And finally, we show a result on the hardness of learning ReLUs. The hardness result is on the Boolean domain. So we show that if there is a polynomial runtime algorithm in the error parameter and the input dimension, then learning sparse parities with noise can be reduced to this problem, which shows the motivation of while working on the unit ball is kind of interesting. The positive aspect we get from that is because these functions depend on the scale. So working on the Boolean domain, the norm becomes higher. So for the proof overview, we basically show the existence of low degree, low weight polynomial approximators for ReLU. And then we relax our problem to finding the best fitting polynomial. And since this becomes a highly computational problem, we reduce the running time and avoid the end to the already running time by using the kernel trick. So the inherent theorem that we basically use is learning noisy polynomials. So given a data, you want to fit the best possible polynomial that has a bounded degree and a bounded sum of squares of the coefficients. So we can model this as solving an ERM and then using the kernel trick, as I mentioned before. For technicality, we use a multinomial kernel that we define in our paper. To guarantee reliable learning, we need to optimize two losses. So what we do is, in the ERM, instead of optimizing on the entire, we optimize only on the positive label loss for the positive label loss, and to minimize the zero label loss, we add them as constraints. And then we show that these two generalize simultaneously. Interestingly, we show a lot of applications of these ReLU networks. So once we can learn ReLU networks, we can also learn parameterized ReLUs and noisy ReLUs, which are used a lot in practice nowadays. We can also learn the piecewise linear transfer function, which is used as an approximation for a 0-1 function. And we can also do piecewise linear regression, which is a sum of max affine functions. I'll give an intuition of how we do piecewise linear regression. Basically, we can see that the max of two affine functions can be computed using a single depth, two-depth neural network as follows, where the dashed lines indicate minus weights and the solid lines indicates positive weight. And if you want to compute the max of a constant depth, max of k functions, then we can just compose these in the log k depth and get a neural network. And since we can learn a constant depth network, we can do this too. So I would like to conclude with some open questions that this leaves us. We still have an exponential dependence on the error parameter for the case of ReLU. So an interesting question is, under what conditions, the weakest possible, can we actually guarantee polynomial time learnability? Also, our output is improper. So it's not exactly outputting a neural network. So is there a way to make this output less improper and still output some sort of a neural network, maybe additional layers? And can we actually show that techniques that are used in practice nowadays actually achieve similar guarantees under certain assumptions on the distribution or the input? In upcoming work, we address some of these issues. We show some polynomial time learning of ReLUs under assumptions on some marginal distribution on X. And we also show polynomial time learning of depth-3 sigmoidal networks in a different learning model. Thank you.
For the derivative results, learning the networks and the piecewise polynomials, are those also in the reliable?
No, mostly agnostic. We can do it in reliable too, but some of them don't make sense in the reliable setting. Like a sigmoid doesn't make sense of a zero label and a positive label, so they work in agnostic. Everything works for agnostic too. Yes.
So is the problem to get the exponential dependence in the parameters? That's something that's linked to the fact that say univariate polynomials are not good at approximating the absolute value function uniformly, for example. Is that this kind of problem?
They actually do approximate, so we need degree 1 by epsilon to approximate it. And then how the 2 to the 1 by epsilon parameter comes is that when we try to bound the norm of the sum of the squares of the polynomial approximator, that the bound we get is 2 to the 1 by epsilon. So either there can be an improvement in that, but as far as my intuition goes, I don't think we can improve on the polynomial approximator's weight. So maybe some other technique can be used to improve the dependence.
Any more questions? Okay, thank you.
Thank you.